Welcome to today's Explainer. We're going to do something really cool today. We're reverse engineering dynamic programming. We're starting right at the foundational principles and scaling all the way up to modern deep learning applications. The goal here is to unpack this totally intuitively. We want to show you exactly how working backward actually authenticates our smartest decisions. So even if you're brand new to the math, you'll grasp the engine driving it in no time. Let's dive in.
So here's our roadmap for today. First, the principle of optimality. Then, unpacking the Bellman equation, followed by the contraction mapping theorem. After that, we'll hit the neoclassical growth model, the curse of dimensionality, and finally, enter deep learning.
All right, let's jump straight into Section 1, the principle of optimality. To really get this, we've got to meet the mathematician who formalized it back in the 1950s, Richard Bellman. Fun fact, he actually chose the word programming instead of mathematics, just to avoid offending a politician who was visiting his corporation at the time. Wild, right? But the name stuck. Bellman's famous principle of optimality basically tells us that inside every massive, complex decision is a nested series of smaller, perfectly optimal subproblems. It's kind of like a road trip. If the absolute fastest route from New York to LA goes right through Chicago, well, then the route you take from Chicago to LA absolutely must also be the fastest possible route between those two cities. If it wasn't, your overall trip just wouldn't be optimal.
So, how do we actually solve these massive problems? Well, we use a highly intuitive method called backward induction. And the trick here is to literally move from back to beginning. We start at the ultimate end goal, the terminal state, and step by step work our way backward. You figure out the absolute best move at the very end, then you step back one single period to find the best move leading to that end, and you just repeat the whole shebang. By working in reverse, we take this seemingly impossible massive sequence of choices and break it down into single, totally manageable decisions.
Moving right along to Section 2, unpacking the Bellman equation.
Okay, now that we have the intuition of working backward, let's look at the actual mathematical engine that powers the whole thing. First up, we need to define the value function. Think of this as a tracker for the absolute best long-term outcome we can achieve from wherever we currently are. It basically maps out the highest possible value our objective can reach, assuming, of course, that we make perfectly optimal choices from this exact moment forward.
And that brings us to the legendary Bellman equation. It's amazing how elegantly this balances our choices. We want to maximize our total value, which we call v of x. To do that, we look at two parts. We add together u of x comma y, which is basically the immediate sunny payoff we get today, plus beta times v of y, representing the discounted long-term optimal path of tomorrow. So we're literally just weighing the immediate reward right now against the absolute best continuation path for the future.
That takes us to Section 3, the contraction mapping theorem.
Now, here is the catch. Because the value function shows up on both sides of that equation, it's recursive. So how do we know it doesn't just loop endlessly into infinity? Well, we authenticate it using something called the contraction mapping theorem. You might also hear it called the Banach fixed point theorem. Think of it as an iterative shrinking process. Picture an inward spinal. If we treat our equation as a machine that takes a guessed function and spits out a new one, and that machine physically shrinks the distance between our guesses every single time, we are mathematically guaranteed to eventually hit a unique mathematical truth, a single undeniable optimal policy.
But the really crucial part here is how we guarantee that inward shrinking actually happens. And it all comes down to our discount factor, beta. For this to work, beta must be strictly less than 1. In everyday terms, this just means human nature naturally values $1 tomorrow slightly less than $1 in our pocket today.
Mathematically, multiplying by that fraction physically forces the distance between our successive guesses to compress at a predictable rate. It guarantees, without a doubt, that we find the truth. To make checking all this super easy in practice, the brilliant mathematician David Blackwell gave us two really simple conditions. First, monotonicity, which just means if we put a larger value into the equation, the result strictly moves upward, never backward. And second, discounting, scaling those future values down by a constant factor. If our model passes these two quick checks, boom, we instantly authenticate our backward induction process.
Section 4, the neoclassical growth model.
All right, let's see how this engine actually drives one of the most famous models in macroeconomics, the Cass-Koopman's optimal growth model. In this setup, an entire economy uses the Bellman framework to balance consuming apples today versus saving the seeds to plant for tomorrow. The main goal here is to find the unique saddle path, that precise, beautifully curved trajectory leading straight to the optimal steady state. If you start with way too little capital, the optimal sequence tells you to save and monotonically grow right up to that perfect, balanced equilibrium.
But what if we set this up with a finite horizon? Like the economy definitively ends at a specific date t. Then we see these absolutely fascinating turnpike dynamics. It's exactly like a road trip. The optimal path rapidly accelerates up to the steady-state turnpike, cruises along it at top speed for almost the entire timeline, and then, right at the exit ramp, capital drops off incredibly sharply as the economy just consumes everything right before the horizon ends. It is a brilliant visual representation of working backward from a terminal state. Which brings us to Section 5, the curse of dimensionality. Despite its sheer brilliance, Bellman's framework does have a fatal flaw. In fact, Bellman himself coined the term curse of dimensionality for it. You see, when we try to solve these problems numerically, we usually map out a grid of all the possible states. But the second you add more variables, say tracking not just capital but employment, inflation, and maybe some random productivity shocks, the number of grid points you need explodes exponentially. It very quickly becomes literally impossible for even our most powerful supercomputers to solve.
But there's a solution. In Section 6, enter deep learning. Fortunately, cutting-edge technology is finally riding to the rescue. If you compare the two approaches, classical dynamic programming gets hopelessly bogged down trying to calculate every single intersection on a massive grid, even the highly unlikely worst-case scenarios. Modern deep learning, on the other hand, entirely ignores the grid. It uses neural networks as universal approximators to learn the continuous surface of the value function, rather than trying to painstakingly memorize billions of discrete, individual points. So deep learning actually tames this curse by strategically focusing only on the most probable, typical regions of the state space. And here's the real kicker. The math here is like magic. It shows that a neural network's approximation error rate scales at O of 1 over m, regardless of the dimensions. M is simply the width of the network. Crucially, this means the error rate does not get worse as we add more complex dimensions to the economy. It literally breaks the exponential curse.
And this brings us to a really provocative conclusion, which is the main thing I want you to take away from this explainer today. With neural networks finally breaking Bellman's curse, allowing us to compute models with dozens of intersecting variables without frying our computers, what incredibly complex economic mysteries are we now on the verge of unlocking? By finally being able to authentically work backward from hyper-realistic future states, the possibilities are, well, they're practically limitless. Thanks so much for joining me. Keep questioning and keep learning.